Hello guys, how are you? This is Hamsawiya once again. We are continuing with our motion graphs. So in this lesson, we are going to be looking at speed time graphs. And as usual, we will start by looking at the slope of such graphs and calculating it. That is the gradient. And the formula for gradient is change in y over change in x. G is equal to y2 minus y1 over x2 minus x1, right? So we're gonna be choosing 2 points now. So any two points here. Which points can we choose? We like choosing easy points, really. So we'll choose, this is only points that make sense, really. 1, then this being point 2, right? So we are going to draw a triangle here, the broken line, to show what we are doing. So this is our triangle from 2 all the way to point 1 here, right? Now let's go on and calculate the gradient, which is the slope. Well, y2, what is the value of y2? y2 is the value of y at point 2. Where is point 2? This is point 2. Where do we get y values? On the y-axis. Remember, this is the y-axis. This is the x-axis. So what we get here is 30 as y2. 30 minus y1. What is y1? The value of y at point 1. Where is point 1? Here is point 1. So the value of y is here. It happens to be 0. It happens to be 0, right? And what are the units? The units are meters per second. The units are meters per second. Well, x2, that is the value of x at point 2. Here is point 2. Coming down vertically to x-axis, we get 10. That is 10 minus x1. What is x1? The value of x at point 1. Where is point 1? Here is point 1. X-axis, we get a 0. So this is 0. Brackets. What are the units for the x-axis values? This is time in what? In seconds. So I'm writing seconds here. Yeah, I hope by now we notice why I used a different color, because blue is for y values with the units being for y, and green is x values and the units, right? So remember, meters per second can be written as meters per second or meters per second. Same thing. Normally we don't use this one. We don't use this one because it takes so much space. If you use this one, that means this line now you won't use this line. So that will take up a lot of space. But in this case, I've used it because I want us to see what really happens, right? So where are we now? We want to compute these, and the answer will be 30 minus 0, that is 30. 10 or 30 meters per second. Meters per second. 10 minus 0 is equal to 10. But the units, remember, I can't leave it out. It's still there, right? That's it. So what do we do from here? What do we notice? We notice that this, there is S, so they have to square. S times S, they have to square. So we will get 30 over 10 meters is still there. S times S is S squared. What do we get from here? This is 3 meters per second squared, usually written as 3 meters per second squared, which is similar to 3 meters per second squared. Same thing, right? Same thing. That is the value of G, and this happens to be what we call acceleration. This is acceleration. So what do we conclude? Because these units are for acceleration, the conclusion is, in a speed time graph or velocity time graph, what we get is the acceleration when we calculate the gradient. So the slope of a velocity time or speed time graph gives us acceleration. In a speed time graph, if we calculate the gradient or the slope, we get acceleration. Well, from our calculations, this is what we got. G is equal to 3 meters per second squared, and we said that is the acceleration. Then in conclusion, the slope of a velocity time graph is the acceleration, right? Let's now calculate the slope of this other graph. The slope, remember the slope, which is G, is equal to y1 minus y2 over x1 minus x2. Then we have to choose 2 points, being point 1 and point 2. I'll choose this as my point 1, put it in brackets, and choose this one as my point 2 and put it in brackets. Then we go on and substitute what is y1, that is the value of y at point number 1. This is point number 1. Y, values on the y-axis, that is 30. Put it in brackets, minus y2, the value of y at point 2. Where is point 2? Here is point 2. What is the value of y here? That is 30 once again, no change at all. And this is in meters per second. Everything divided by change in x. x1, this is the value of x at point 1. Where is point 1? Here is point 1. Where are the x values? Vertically downwards. Tada. Then that is 25 minus x2. x2 is the value of x at point number 2. Where is point number 2? Here is point 2. Then going down to the x-axis, I will find the value of x vertically downwards. Yes, this is 5, right? And the units, seconds, right? And once again, 30 minus 30 is 0 meters per second divided by 20 seconds, and the answer is 0 meters per second squared. This is the slope. Which is also called G gradient. This is the slope. So what does this mean? This acceleration is 0. What is acceleration? Acceleration is the increase in velocity or the decrease in velocity per unit time. This basically is the change in velocity per unit time. So that means the velocity is not changing. When the velocity is not changing, when the speed is not changing, that means there are two possibilities. Either the object is at rest or the object is moving at a constant speed. So which one? Is the object not moving, or its speed not changing but moving? Oh, how do I know? Well, the graph is here at state, and it is state throughout. Even as time goes by, the value of the speed is still at state. That means the speed is not changing, but the object is moving, which means this is the what? The constant speed, the uniform speed. The object is moving with uniform speed. How about this one? Here what we see is the gradient is just a straight line, right? The graph is just a straight line. This means the acceleration is constant, or the speed is changing uniformly. The speed is changing uniformly, or we can just say the acceleration is constant. Now let's go on and look at other typical graphs, speed time graphs or velocity time graphs. Well, here are the typical velocity time graphs that we need to look at. And here we have the motion of this object with uniform acceleration. How do we know that? If we see a straight line, the motion is uniform motion, right? Uniform acceleration. So let's start with the first graph. Let's start with the first graph. We'll call it A. This is B and this is C. And with the first one, we see that the gradient or the slope is 0. So the slope is 0. And remember, the slope in a velocity time graphs represent what? Acceleration. It represents acceleration. So what can we say about this speed? There is no acceleration. When there is no acceleration, that means the speed is the same. The speed is not 0. The object is not at rest, because this is 0, this is 0, this is 0. This, as you go up, these values cannot be zeros as well. So the object is moving, but at a uniform velocity. This is uniform velocity or uniform speed, right? So this is how we describe it. This object is moving with uniform velocity or constant velocity. Uniform or constant, right? Uniform velocity. This is uniform velocity for graph A. Let's look at B. What can we say about B? At B, what we notice is it has a slope. The slope is a straight line. The slope is a straight line. When it's a straight line, this slope is not changing. So the slope is constant because it's not changing. When it's not changing like this, we see that it is constant. And what is constant here is the acceleration, because the slope represents what? Acceleration in a velocity time graph. So constant acceleration. Constant acceleration. Constant acceleration. We can also define this as, we can say the velocity is increasing uniformly. Yes, velocity is increasing uniformly. How about C? C we say is a constant deceleration. You can also say the velocity is decreasing uniformly. The velocity is decreasing constantly or uniformly. Constantly. Yes, it's decreasing by the same amount every second. Yes, now let's look at other types of graph with a non-uniform acceleration. Well, here they are. Non-uniform acceleration graphs. We are still looking at velocity time graphs, and call this, let's see, D, call this E. So for D, what do we see with this slope? This slope is increasing. The steepness of the slope is increasing, right? The steepness is increasing. Therefore, the slope is increasing. It's becoming harder. If you were to climb here, you'll notice that it becomes harder as you go high up. So this slope, as this slope is increasing, we remember that the slope of velocity time graph represents acceleration. Therefore, increasing acceleration. Increasing acceleration. With this one, the slope is decreasing. For the graph E, the slope is decreasing, therefore decreasing acceleration. That's it with graphs decreasing acceleration for E, right? We now look at calculating distance traveled in a velocity time graph, right? Let us put in the values. So the numbers are in. Now let's do the calculation. And how do we calculate that? The distance traveled in a velocity time graph is the area under the graph. The area under the graph. So the graph starts here. The graph ends here. So under the graph is this area. This is the area under the graph. This is the area under the graph. This is the area under the graph. So this is the area under the graph. So actually it's up to here. We have to be precise there. So what is this? This is 0, 2, 4, 6. So midpoint between 4 and 6 is 5. This is 5. So what is the area under this graph? This area is the area of what? This looks like a rectangle. So the distance traveled A is the area of a what? A rectangle, which is length times width. And the length from 0 to 5. That is 5, right? Multiplied by the width. This is 0 to 8. Multiplied by 8. And what do we get? This is 150 meters. 150 meters. That is the distance represented by the area. So it's just S is equal to 150 meters. So that's it. That's the distance traveled in a velocity time graph, is the what? Area under the graph. We now shift our attention to graph B, and here we see that this shape, the area under the graph, represents a trapezium. We could use a trapezium straight away, but we are going to choose dividing this shape into two, a triangle and a rectangle, because for most of our students, really, we have noticed that they struggle when it comes to the area of a trapezium. Well, this is how we have come up with two shapes, this being A, this being B. So let's start with A. Distance traveled is the area under the graph for diagram A, which is a rectangle. And a rectangle, we remember very well, the area of a rectangle is half base times height. Half base times height. Well, half times base. What is our base? Base is from 0 to 4, which is 4. Then height is from here to here, which is 20. 20, right? Then what do? Half times 4, we can just divide here by 2 and here by 2 to get 2. So it's 2 times 20, which is 40 meters, right? Area due to a triangle is 40 meters. Then area due to B, what is this? This is a rectangle, length times width. Length times width. Okay, for this one, let me include units so that we see how we come up with meters, because it's not kind of magical. So length, which one should we choose as length? The long side, which is 20. This is 20 meters per second. 20 meters per second. Times width. This is time in seconds. Right? It's from here to here is 20, but for this one is from here to here, right? What is this? 10 minus 4. 10 minus 4 is equal to 6. 6 what? Seconds. So is 6 seconds. And what do we get? S cancels S. Just like numbers, just like zeros. Then we have 6 times 20. 20 times 5 is 100, plus 20 is 120. 120, we are left with M for meters, right? Yes. So the total distance S is equal to S due to area A plus S due to area B, which is 40 meters plus 120 meters, which is 120 meters. So this is the area under the graph. So you could have used the area of a trapezium straight away, but we find that most of our students are struggling with that. That's why we divided these into two shapes, right? A triangle and a rectangle. So that's it about distance traveled in a velocity time graphs. The next thing that we need to do now is to look at questions, be able to solve questions, right? Thank you.